Depending on the applications, sometimes we need to convert an analog data to its digital version or a digital data back to analog version. So, for these applications, we need converters. There are two types of converters: analog to digital converter and digital to analog converters. The first one is analog to digital converter or ADC. It changes an analog voltage into its digital equivalent, analog to digital. So it will change an analog voltage or a continuous voltage to a digital voltage or a discrete voltage. Now, second type of converter is digital to analog converter. So it changes a digital value back to its analog voltages. So a digital converter will be changing a digital data or discrete data to analog or a continuous wave data. So it is called a DAC or digital to analog converter. Now here we will discuss about different types of analog to digital converters. So as I told, analog to digital converter means it convert an analog voltage to its equivalent digital signal. A number of methods can be used for doing A to D conversion. So mainly analog to digital converters are classified into two general groups based on the conversion techniques. One is comparing the given analog voltage with internally generated reference voltage. Such type includes successive approximation type, flash, delta modulation, adaptive delta modulation type converters. So there are different types of analog to digital converters. So in that, the successive approximation, flash, delta modulation, adaptive delta modulation type all are based on the given analog voltage will be compared with an internally generated reference voltage. Now, another one is changing analog signal into time or frequency first and then comparing these two parameters against the known values. That is another type of A to D converter. So that means it will change first your analog signal to time or frequency and then compare it with a known or reference known values. So normally this type of converters we can includes integrator converters or voltage to frequency converters and all. We can make such type of AT converters with that. So mainly these two methods what we are discussing here, dual slope conversion, ladder network conversion, both are two different types of analog to digital converters that is of this category. First the analog signal is converting to time or frequency, then it will be comparing with a known parameter. So the first type of A to D converter what we are discussing here is a dual slope A to D converter. So it is an indirect method for A to D conversion where an analog voltage and a reference voltage are converted into time periods. Analog input and reference voltage both are converted into time periods by an integrator and then it is compared and measured by using a counter. Speed of this conversion is slow, but accuracy is very high here. So now we'll come to the operation of the circuit. So as you can see the block diagram, it consists of an integrator, a comparator, a control logic. This control logic what is shown here, it is basically an AND gate. and a digital counter or a binary counter. These are the essential means blocks inside a dual slope conversion. So your analog input voltage, which should be converted to your digital output, should be provided here to the integrator, and then it is given to a comparator and it will compare it with a reference voltage. That output will feed to a control logic AND gate. So one input is the output of comparator, another input of AND gate is clock. Based on that, it will count in the digital counter and the corresponding digital output for this analog input be getting over here. So I'll now explain the detailed operation of a dual slope analog to digital converter. So here the first one block is the integrator. The input of the integrator is connected to an analog voltage which is to be converted to the digital. So that is VI through an electronic switch. So if it is connected to the VI, that corresponding digital voltage of this analog will display over here. So otherwise it is connected to V reference, normally will be taken it as 0 volt. So what happens when it is connected to analog voltage? As it is an integrator, when it is connected, this is the capacitor C of the integrator. So when it is connected to the analog voltage, it will charge. How much is your analog voltage? That will charge to a fixed time interval. See, I'm just marking that time interval as say T1. So charging time interval, I'm just marking it as T1. So it will charge from 0 to T1. So what is the expected output V01? We know what is the integrator expression. Integrator is 1 divided by the resistance, I am marking it as say R1. The capacitor I am marking as C1. So 1 by R1 C1 integral VI, the input, into dt. Integral over the same T0 to set T1. So 0 to T1. So it will be, we be getting it as VI into dt become T over the time 0 to T1. So it will be T1 divided by R1 C1. So that is your integrator output. See, if you are applying a large voltage, the for the fixed time interval, it will charge to the maximum. V01 will be the maximum. If it is a smaller input voltage, it will charge to the minimum value, so it is smaller input voltage. The one thing you have to keep it in mind is this integrator is connected to the analog input voltage for this fixed time interval. Say it is marked as T1. After T1, immediately it is connected to the reference source 0 volt. So till T1 it is being connected to the input voltage and it will store, or the capacitor will charge to the maximum value. Now after T1, this switch is now changes to V reference. So your capacitor starts discharging. So now it will come down till 0, till V reference. Say I'm marking that count interval as say T2. That means if this voltage, small voltage means it is small time interval little itself, it will come back to 0 reference. If it is a medium voltage, it will take little more time. If it is a large voltage, large time it will take to come back to the V reference. So depending on the time how much it is taking, that thing will be converted here as the digital output. So now what happens? Now you see here this output is given to the comparator. The negative voltage of the comparator is a V reference. So now when it is the voltage discharging interval, normally the counting starts in this interval. The fixed time charging we are not taken into account. So discharging time, when say this voltage, it is charged to the maximum. Now it starts discharge. So as it is discharging to 0, to the V reference, the till that comparator output plus terminal output will be higher. So you will get a high voltage here. Now, so it is an AND gate. This control logic is an as the comparator output is high. When each clock comes, it will start counting 1, 2, 3 like that. It will count. How much time it will count? It will count T2 time when it come back to 0. If it, however be the voltage. If this is the voltage, it has taking long time to back to 0. This is the voltage, it will take slightly less time to come back to V reference. If this is smaller is the voltage, it will take very small time to come back. That is your T2. So T2 time this AND gate will be on, and that time your whenever a clock comes this binary counter will start counting. So till the time T2. So whole T2 time this binary counter will count, and that will be at the end when this output is equal to 0. That means it will go below that V reference. This will switch to 0 comparator output. So the AND gate is disabled. It will stop counting. So that will be the corresponding digital output of your analog voltage. So we can write the discharging time, how much time this integrator will take down, ramp down, that we can write it as, that is equal to, again that means that time should be equal to VR, say the it will reach to the reference V reference into taking time will be T2 divided by the same resistor R1 C1. That is the time taken to come down, the discharge time. So that will be the corresponding output voltage. So now we know that V01, this should be equal to this value. So we can write here as V01 is VI T1 divided by R1 C1 should be equal to V reference into T2 divided by R1 C1. See R1 C1 both side I am cancelling. So VI T1 should be equal to V reference into T2, or I can write T2 as T2 is equal to VI divided by V reference multiplied by T1. So the T2 is VI is the analog voltage divided by V reference into T1. So in this equation, T1, it is the fixed time interval to integrator to charge, and V reference, these both are fixed value. So we can say that your time T2 is directly proportional to the analog input voltage VI. So the binary digital output of the counter gives the corresponding digital value for the time period T2, and which is directly proportional to VI. So the actual conversion of analog voltage V input into the digital count occurs during T2 second. So the control circuit connects the clock to the counter at the beginning of T2, that is after just fixed time interval T1, and the clock is disconnected at the end of T2. Thus, the counter condense is the digital output of exactly what is your analog input voltage. So, we can write your digital output as, you can write our digital output as, it is the counts per seconds times your T2. What is T2? It is VI by V reference into V1. So it is equal to counts per second into VI by V reference into T1. So this is the digital output corresponding to your analog input voltage Vi. So the counter output then connected to any appropriate digital display, you'll be getting the proper digital value of the given analog input voltage.